AP Calculus AB, Unit 9, Day 4 lesson. So we're going to bring back one-dimensional motion, rectilinear motion, motion on a line, and use some of our new tools to be able to do some new things with motion, with integrals. So we're going to talk about the idea of distance and displacement. So displacement is the total just change in position, the overall change in position. So, if we're looking here, we could go ahead and say, okay, well, from start to finish, the finish point is -5 behind the starting point. It doesn't really matter how we got there, okay? It can be negative, it can be positive, it can be 0, okay? Essentially, it's the final resting point minus the starting point. That's it. Just where you end minus where you began. That's displacement. Distance has to always be positive. You cannot have negative distance, okay? And distance does care about the path you took. Displacement doesn't care about how you got from the start to the end, just where are you, where did you start? But distance would be like, okay, well, that's 5. Here's another 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 5. 5, 10, 15, 20, 25, 30, 35. The distance traveled is 35 units. It's got to always be positive, okay? Now, let's start to try and connect this more to our equations for position, velocity, acceleration. So displacement is S final position minus S initial position. It's that simple, okay? So position. Now, there is a very special case where displacement and distance actually come out the same. Can you guys think of an example where distance and displacement would be the same? For instance, if we started here and we ended here and we never changed direction, then displacement would be final spot minus initial spot, which would be 15, which would also be your distance. Your distance would equal 15. So this would be the one special case. And the thing that's special about it is that you're moving to the right the whole time. If you're moving to the right the whole time, distance and displacement would be the same. If you flipped it around, displacement would be -15 and distance would still be +15. So it wouldn't work. It's got to work left to right the whole time. But that's a very special case that we're probably not going to really see. So have to be moving in positive direction the whole time, forward. Anyways, it's really just something to think about. Usually they're going to be different. Okay, let's see if we can start to finalize this more. Let's think of it, instead of final time, initial time, we'll say time 1 and time 2. So it's going to be position at time 2 minus position at time 1. Now, an interesting thing is that hopefully some of you guys are thinking, I don't know, that kind of makes me think of like what we get when we integrate things. If we were to integrate velocity, we would get S, right? And then we'd plug time 2 in first and then minus time 1. So actually, another way of finding displacement is by integrating the velocity, which is the accumulation of all the changes. So displacement is really like the total change in the end. And if you integrate the derivative of position, velocity, you're going to get the total change in the end. So this is just another way to get displacement. Now, if you can just simply plug the numbers in, that's a lot easier, right? Distance Now, the way we're going to find distance is when you integrate velocity, positive changes, negative changes, they cancel each other out. And you just get like overall the difference in the end. But if you want all the changes to be considered positive so that they all add up and they all come out positive, the simple way of doing that is by taking the absolute value of the velocity. That would force all the changes to be positive and they would all add up. Now, by the way, this is the same thing as speed. So when you think distance, you think integrate speed, okay? So we need positive velocity to get distance from displacement. So it's kind of like the same idea, but we're going to force everything to be positive. And the way to do that is to use an absolute value. Now, luckily, we've recently learned how to integrate absolute values. So that's going to be handy. So let's try some examples. So here's a position function, and we want to find Johnny's displacement from 0 to 5 and distance from 0 to 5. Now, displacement's easier for sure, way easier, because all you got to do is you got to say, all right, S5 minus S0. So if we plug 5 in, we get, this is, I don't know if we should do the work for these separate. Might be worth it. 125 minus 150 plus 45 plus 1, negative 25, it's going to be 21. So this is going to be 21 minus 1 is 20. That's the displacement. All right? Not bad. Now, distance is a lot more complicated because we have to integrate. So we have to integrate 0 to 5 of the absolute value of velocity. So we're going to have to use our integration of absolute value skills that we've recently been doing. Now, we don't even have the velocity yet. So we would have to find the velocity. The velocity is 3t squared minus 12t plus 9. Right? And then you guys remember, the way we do this is we got to break this up into its positive and negative chunks, integrate them separately, fix the negative chunks. The way we do that is we find the zeros first. And then we do a line check. That's the quickest way. Far right, positive, positive, negative, positive. So that tells us that we need to integrate 0 to 5, 0 to 1, drop the absolute values, 3t squared minus 12t plus 9. And then we're going to do 1 to 3, drop the absolute values, 3t squared minus 12t plus 9. And then 3 to 5, drop the absolute values, put parentheses still, 3t squared minus 12t plus 9. The negative part's got to be fixed, so this needs an extra negative. Otherwise, if they're positive already, we just add them. Now, I'm going to wait. I'm not going to do this work right now because, we should be able to do it. It's going to be pretty tedious, So I kind of want to show you guys a way of making the work a little easier, okay? You don't have to. And in fact, this little trick can help you on integrals of any kind of absolute values. It doesn't just have to be motion, but so far, this is what we have, okay? And then we would keep going. But let's look at if there's some ways to maybe make the work go a little quicker and easier. Because by the way, one of the big things here that's tedious about this is we're integrating the same function 3 times. We're doing the same work 3 times. And then we're plugging 1 in, and then we're plugging 1 in twice. Same thing. And then we're plugging 3 in, and plugging 3 in twice. Same thing. There's a lot of work here that's repetitive. So maybe there's a way we can take advantage of that and get rid of the repetitive part of it. Okay? So let's just take a step back from that. We'll come back to that problem. Let's just look at something a little simpler. So here's a problem, kind of like the ones we've been drawing. Let's say that this is time 0, time 1, time 2, time 3, time 4, time 5, time 6, time 7. You guys are all right with that? I'm going to say, okay, well, let's just make a table of all the positions here. Maybe this will help us find the total distance because, before we're like, oh, this is 5, 5, 5, 5, 5, 5, 5, and we added up and it was 35. Okay, so maybe we can kind of take that approach, but in a little more organized in a table because we're not going to draw this crazy picture every time. So at S0, it's at 5. At 1, it's at 10. At 2, it's at 5 again. At 3, it's at 0. At 4, it's at -5. At 5, it's at -10. At 6, it's at -5. And at 7, it's back to 0. And we can say, you know what? Let's just find the distance between each of these points because that's what we kind of did before. We're like, well, this is 5 and this is 5. Like we were finding the distance between those points. So the distance between 5 and 10 is 5. 10 and 5 is 5. 5 and 0 is 5. 0 and -5 is 5. -5 and -10 is 5. Distance is always positive. It's the absolute value of the difference, by the way. 5, 5. If we add all these up, we get 35. Right? I mean, that's what we did before. This example is exactly the same as what we did in the previous lesson. Okay, so that's cool. This table thing kind of organizes it. But do we really have to do all these points? And what about the points in between? We really could keep breaking this down. But really, there's really just certain points that really make the difference. We don't need all the points. Which points are the ones we really need in our table to get the right number? If we skip the wrong ones, we'll get the wrong answer. Here's the key. We just look at where it changes direction. And for a while, we've been calling these turning points. They're where the velocity equals 0. Okay? And so right here, this is a turning point. Here, this is a turning point. Those are the only two turning points. Those are really the only points we need in addition to the beginning and end. So if we do that, I'm going to make a new table over here. See if we can take advantage of this. So we definitely need 0 and 7 still. We still need the starting point and the ending point. But we want the turning point. So that's time 1 and time 5. These are also kind of like critical points, right? And if we just plug those values in, at time 0, it was at 5. At time 1, it was at 10. At time 5, it was at -10. At time 7, it was at 0. And if we do the distance between these is 5, distance between these is 20, distance between these is 10, guess what we get? We get 35. Much faster, right? So let's see if we can take advantage of that. Now, there's something else cool about this. So this is what we did before. This is what we got before. Let's make a table. And we've already found the turning points, okay? So 0 and 5 are your beginning and end points. And the turning points where we decided to break it up at 1 and at 3, okay? Now, S right here is going to be the integral of velocity, which was 3t squared minus 12t plus 9. But here's the cool thing about it. Because we're doing this table, we're just going to do it once because it's going to be the same thing all 3 times. We're going to take care of all these in this nice little, cute little table. 3t cubed over 3 minus 12t squared over 2 plus 9t. Okay? And we're going to plug these into that. So if you plug 0 in, you get 0. If you plug 1 in, you get -5, you get 4. If you plug 3 in, you get 27. 27 minus 54 plus 27, which is 0, by the way. Okay, you plug 5 in, you get 125 minus 150 plus 45 is 20. And we just find the distance between these 4, 4, 20. The answer is, for distance, the answer is 28. Okay, now that's what we would have got if we did all of this work. We would have eventually got a 4 from this, a 4 from this, a 20 from this, and it would have been 28. So this is kind of handy, and we can use this for any integral of absolute values to cut down on the repetitious work. We're doing the same work. We're integrating the same thing, but just once. We're plugging in all the same limits, 0, 1, 3, and 5, but we're just doing them once instead of twice and twice. And it's in a table, which kind of, I feel like, makes it a little easier to follow. I mean, otherwise this work would have been very tedious, okay? So kind of an interesting thing. You don't have to do that. You can just do it the way we've been doing integrals of absolute values so far. But this is a pretty cool trick, I think. You got to make sure you understand how to use it. Is distance always equal to or greater than displacement? Yes. It's always equal to or greater than displacement. You can't have a distance that's less than displacement. That wouldn't make sense. Can we use this strategy on problems that aren't position velocity problems? Can we just use it on any old absolute value? Yeah. So we actually did this problem a few lessons ago. You still got to figure out where the zeros are. But one of the cool things about this that lets you off the hook is you don't need to do the line check anymore because we're just going to use the table. You could do the line check, and it could help you on certain problems, especially problems that have ugly answers. But we're going to probably kind of just do it in our head. So we're going to make a table. Okay, now here we're going to drop the absolute values like we would if we were going to integrate it. Antiderivative x squared is x cubed over 3. It's 2x squared over 2. We're going to plug 0, 2, and 6 in. Plug 0 in and get 0. You plug 2 in and get 8 thirds minus 4, which is going to be negative 4 thirds. And you plug 6 in and you get 72 minus 36 is 36. You could write this as a mixed fraction, or you could write this as as a fraction over 3. You at least comes denominator. And when we're doing absolute values, we're trying to force these answers to come out positive, which is just like distance. What's the distance between these? Positive 1 and 1/3. What's the distance between these? 37 and 1/3. So if you add it up, what do you get? 38 and 2/3. That's the answer. Now, if you compare that to the way we did it before, it's a lot less work. So, the way we did it before is we did this, and then we did a line check, and you can still do line checks to help you out with these tables if it's a little confusing. We tested x equals 3, which was positive, negative, positive. And, so this is what we did before. I'm not even going to do all of it. I'm just going to set it up. So we said, okay, we've got to do 0 to 2, x squared minus 2x dx. And it's negative, so we had to fix it by adding negative. And then we did 2 to 6 of x squared minus 2x dx, right? And then we started integrating these and plugged all these in, which is all the work we've done here, but it's just much more compact. Okay? Now, here's the cool thing. Your calculators are really good at this, but this is a general shortcut. This whole table approach is a shortcut that works for any integral of absolute values. So, kind of cool. All right, try the worksheet out.